Cool. Let's do it. Alrighty, so, send me an attendance ping first up, because I've been forgetting to do these, and I forgot to do them at the end of class, but pretty much people are coming to class, so I'm not too worried about it. And I think a few people are a few minutes late, so I'll ping again later. Alright, let's see. What are we talking about today? Let's start with questions on homework 7. Now, we haven't gone through most of the indirect file stuff, but if you've had a chance to look at it, any questions so far on your last homework? And that's your last homework for the course, by the way.
Can we treat it as if it's a pointer, but we only have like 2 or 3 variables to store as a pointer?
Basically, yeah. We have 3 sets of registers, so we have basically 3 pointers we can do what we want with, and we can look at the thing they point to.
I also have a question about are we going to talk about the table read stuff? Does that have anything to do with the arrays?
No, we're not going to get into that probably. Table reads are the last class of instructions on the PIC, and they're actually used kind of like the indirect registers, but they're for manipulating the program memory. And everything that we've done so far manipulates the file register memory, and these indirect registers also manipulate the file register memory. The program memory is where the actual machine code for your program gets stored. We can manipulate that. That's what the table read instructions are for, and that's fun to play with. Say again?
So it's kind of like reflection.
Yeah. Or introspection. So those are fun to play with. I think they probably work well in the simulator. I haven't tried them. I've used them on hardware, and they work as advertised. And it's fun, because self-modifying code is, you know, how everything we do with computers works, right? Ultimately, operating systems don't do their thing unless they can modify the code of the OS. So that's fun stuff to play with, but that's beyond our scope. And if you want to play with it, make sure you just read the sections in the book, because there's like this secret handshake you have to do to make it work, so that if you accidentally, you know, execute a table read or a table write instruction, it won't have any effect unless you've done the secret handshake first, which involves, you know, writing certain patterns into certain places in a certain order to make it clear that, yeah, I am intending to modify program memory. Otherwise, it's a kind of dangerous failure mode. All right, other questions? Hey, there's my relays.
I know that at the school we have actual physical PIC 18 F1220 chips. Is there like a program where you can borrow one of those, or? Because sometimes I just really wish I had one so I could learn how to, I don't know, do Hello World from scratch.
Yeah, I mean, we have tons of them, and they're really inexpensive. The trickier part, though, is that to program them, you need something called a PIC programmer. And it's, you know, this little USB device. It's about this big. You plug one end to your computer, and the other end you have 6 connection points, and you hook wires up to there to certain pins on the PIC, and use that to load your program in. And those we only have a few of. We only have enough, you know, if people borrow them during lab. So those I don't think we lend out. The PIC chips, if you wanted to play with one, we could give you one of those if we were on campus. These things aren't expensive to buy, though, if you want to mess with them, right? PIC chips cost like $1 a piece or something like that. The programmer is probably $20 or $30, but you can look around on Amazon, and if you're going to do something with PIC chips, it's a fun way to mess with it. But there's other processors out there also, like I say, Atmel's AT328's the chip inside an Arduino. those are basically reduced instruction set machines, and they're pretty accessible to play with.
Is there an easy way to export your code to a programmer from MPLab?
Yeah. Let me see. It's been so long. Well, let me see what this looks like. So when you have a program in, there's this little symbol here with the little square with an arrow pointing down to it. If you click that, basically, instead of running it in a simulator, it'll download your code through a programmer into a physical chip. And when you set up the project, instead of saying you're going to use a simulator, you let's just start a new project. So down here you would say what kind of programmer you're going to use. So we usually use PicKit 3, and so you would select that. And that will build it in such a way that you can eventually download the binary configuration and instructions into your chip. We use simulator because, you know, it's simulated. It's a pretty painless setup, and like I say, pretty fun to work with. And then once you program it once, it's programmed for life unless you change the program. So you can disconnect it, remove power, and then go back later on and put power on it, and it starts running your program right away. Which is pretty sweet. All right. Any lingering issues with Lab 5? All right, well, let's talk about Lab 6. And I don't want to spend too much time on this because it's a lot of reading. But let me talk to you about the kind of higher level aspects of Lab 6. And Lab 6 is actually Lab 7. And so this is your last lab for the course. And this has to do with serial communication. So the basic idea is the following. When you want to communicate with a computer, right? In the old days, what would you do? Well, you'd run a bunch of wires over, and let's say you wanted to send an 8-bit character code. Well, you have 8 wires, character bits 0 through 7. And, you know, you send your information from your teletypewriter or your modem or, you know, maybe an Ethernet connection or something into your CPU. And it can, you know, read these 8-bit values and put them together to form an ASCII code, right? So ASCII is this coding. It's basically an arbitrary coding, but for example, the letter A has ASCII code decimal 65, which in hex is 41, which in binary is that. So if you wanted to send the letter A, right, you would put a 1 right here, and you'd put a 1 right here, and you'd put zeros everywhere else. And that's very straightforward. The downside to that is, you know, you need 8 wires going in, and if you want a character coming out of the CPU, you need another 8 wires, and that's a lot of wires. And when you think about something like, you know, sending information over a phone line, you have, you know, one phone line. You basically have one channel on which you can send and receive something like a tone, right? So we can use a pair of tones to represent a 0 or a 1. We can send 1 bit pretty easily, but to send 8 bits is a lot trickier. If you have a you know, cable, fiber optic, pulsed lights, you know, all these things are really good for sending basically two pieces of information, like on or off, high or low, bright or dark, whatever. Sending bits is easy. Sending a collection of bits is generally more complex. And so this is, you know, a parallel transmission. Generally what we find in the real world is serial communication, where you send just a single bit and you receive a single bit. And, you know, Ethernet communications, wireless communications, if you've played around with any devices using things like I2C or SPI or any of these other protocols, these are all serial in nature. And so you basically get one channel on which you can send information. Well, how do you send something like this if you are only allowed to send a single bit? One way to do this is to multiplex in time. So make yourself a clock. Tick, 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 tick. And if I want to send this number out, let's say we start from the least significant bit, I would send a 1, a 0, a 0, a 0, a 0, a 0, a 1, and a 0. So we serialize this parallel data. And one way to do this is to use, you know, a time base. And we say, okay, so every millisecond we're going to sample this, and if it's high, we'll record that as a 1. If it's low, we'll record it as a 0. A more reliable way to do this is to use a pair of wires, one which would be like a clock, that's a perfectly consistent clock, by the way, and a data line, which might say, you know, send a 1 and then a 0, 0, 0, 0, 0, 1, 0. And the way the system might be set up is every time the clock rises from a 0 to a 1, that's a point where we sample the data line. And it more or less doesn't matter if this clock line is imperfect, if it gets slightly faster or slower, because we're only going to look at the data line when the clock rises from 0 to 1. Maybe it's feeding the clock input on a flip-flop, right? And so here we sample the data as a 1, 0, 0, 0, 0, 0, 1, 0. So things like I2C, SPI, they use this kind of approach where you have a clock line and a data line. But a very old protocol that uses an understood clock is something called RS-232. And this is the protocol that was used on old modems. This was used on old terminals that you would hook up to a computer and so on and so forth. And the PIC processor will speak RS-232, or a version of it. So if you go into the data sheet, and I'm not going to delve into the data sheet too much, but if you go into the data sheet, there's a section Enhanced Addressable Universal Synchronous Asynchronous Receiver Transmitter. So these used to be called UARTs, Universal Asynchronous Receiver Transmitter. Well, it's also synchronous, and it's enhanced, and it's addressable. But basically, this is a way to say, hey, I would like to send this 8-bit number, the contents of this file register, out a serial communication line, and ask the PIC processor to drive that line high or low according to some understood clock. This clock, by the way, is what we call baud rate. So if you find yourself back in time and you're looking at a modem and it's got a baud rate of 1200, it means this clock is ticking 1200 times per second, basically. So it's the frequency at which we sample the data.
Is USB more of like the client device supplies the clock?
I don't remember how the clocking works on USB, because I think it's 4 wires inside. But I think there's an understood clock because I know the original issue with how long a USB cable could be was not signal degradation, it was time delay. Because, a nanosecond per foot. So if you had a 12-foot USB cable, the time delay was great enough that you would get clock skew that would corrupt your signal. But I think the clock is understood in that, but I could be wrong. And it depends which USB. By the time you get to USB-C, it's all sort of extreme. But USB is a really good example of a modern serial device, right? When you hook up a hard drive to a USB port, the data coming out of that hard drive into your PC is coming in serial, 1 bit at a time, right? Even though what you're reading off the hard drive is, 8 or 16 or 32 bits in a chunk, it's communicated serially. So this is like, all the other subsystems in the PIC. It's got a bunch of configuration registers and a register for setting up the baud rate, and protocols you have to go through to begin and terminate a communication. And it's also interrupt driven. You can set it up to say, hey, when you're finished sending a character, generate an interrupt so that I know you're ready to send a new character. Or when you receive a character, give me an interrupt. And now you can set it up to receive, go off and do your business, but when a character happens to come in, you'll get an interrupt and you can go and pick it up. And it's got all kinds of complex calculations for how to set up baud rate and all sorts of good stuff. Is that a question?
The baud rate is the clock, right?
The baud rate is the clock, yeah.
Okay.
So this is the asynchronous mode. This is the RS-232-ish version. Strict RS-232 used something like -12 and +12 volts to represent a 1 or a 0. On the PIC, it's obviously 0 volts or 5 volts because everything is those voltage levels. But the signaling, the coding of bytes in serial is still the same. So we can have a transmit interrupt enable, interrupt flag, interrupt priority. To let us know when the transmit register is ready, and so on. All right, so all of this is spelled out for you in the lab write-up. All right, so we don't need to dig too deeply into the data sheet. So this talks a little bit about what we've just described, right? The basic idea of serial communication. Serializing information, sending it 1 bit at a time, a little bit about baud rate, knowing how fast to sample the input, and so on, all right? So basically, when we want to do serial I/O, we need to set up that, extended UART subsystem, pick a baud rate, tweak the interrupt system if we want to use interrupts, and then we basically read or write special function registers to either send or receive a character. So there's 3 experiments in here. The first experiment is a lot of stuff. So let me suggest how to write this lab up. Okay, the first experiment goes on and on, page after page, in excruciating detail. Okay, I think we've covered every possible contingency in here, which means we haven't, but we've tried. And you don't need to document every single step in here, okay? Remember, everybody doing this lab, everybody looking at your lab report should have already done the first 5 labs. So we say start up MPLab, go to File, New Project, click the Next button. You do not need to put that in your procedure, okay? But the stuff in here that's different, that's what you want to talk about, right? So procedure, created a new project named such and such in the usual way with the following modifications. Talk about the new stuff, all right? So this is all the same that you've always done, right? Put in the processor, choose simulator, MPASM, finish, and so on. And then it starts to get different. So let's see, once you finish, you see a different window, sub-window, echo, header files, important files, blah, blah, blah. That's all the same that we've done every time. All right, so what you are going to do is enter a new file, and when you create it, take a note of what the path is. Okay, because you're going to need to use that. And then this is where we get into the unique stuff for basically we're going to try to use the simulator to pretend that we're sending serial information and to read serial information that's being sent by the PIC and make it so that we can read it. So you're going to want to set some things up under your configuration to enable UART1 IO, right? And you're going to have to go in and check some boxes and so on and so forth. Okay, so don't put all of this in your lab report and don't copy and paste this. My suggestion is, use this to let you go through the procedure, okay? And work through this until you're able to get through experiment 1 successfully. And then go back, sorry?
Should we mention any of this stuff, just like a little bit?
Well, after you've got this working, go back and redo this experiment. But now, make notes for the parts that are different from what you've done every other time. And those are the things you want to talk about, right? So you definitely want to talk in there somewhere about setting up this UART1 IO options, enabling UART1. There's some other things you're going to have to set up, right? So put that stuff in there. Just don't go overboard and say, well, first I had to click on the MPLab icon to start it. And then I clicked on the File button and a menu appeared and I moved my mouse down to New Project. Don't go down to that level, okay? You're not graded by how many pages of lab report you have, and that's just going to be frustrating for you to try to write. So assume that the person reading your report knows how to make a project, right, up through, say, Lab 5. But the stuff that's new, dealing with the UART subsystem and the simulator, document that. And just do it in your own words. Just paraphrase, because there's a lot of detail in here. If this goes wrong, do this. If you find this happening, do that, and so on. So do this once, get through the end of the experiment, and go back, do it again, and record, what you have to do, and write that up in your procedure section. And what you're basically going to do is you're going to create a file with some stuff in it, and you're going to write a PIC program that'll read that file and show you what's inside there. So this is boilerplate code, right? You can take this and put that into the simulator and run it. And then there's all this other stuff I put in to, kind of help. But this is stuff, this is your build project button. This is for running the project. This is continue. This is step, right? You don't need to talk about all that, okay? When I wrote this up, I was envisioning this as one of the earlier labs, I think. So, but you are going to need to know about this run SCL file. All right, so set all that up, and then you're going to simulate the code. And so here you're going to have to do some more stuff. You're going to have to go into the stimulus tab, but this time you're going to choose register injection. So instead of clicking a button to toggle a pin, we're going to actually inject ASCII codes into a pin in serial. So follow these instructions, and you got to follow these really carefully. If something goes wrong, go back to the start, do it over again. All right? And pay attention to bold-faced things also, because I bold-faced them for a reason. All right, build it up and run it, and what you should see is that as you run through your code, each time that you read from the special function register for receiving a character, you should see the successive characters of, hello world or whatever you put inside your test file. All right, so record all the values observed for at least one full cycle. That's simulating input to the PIC processor, and then we want to simulate output. So we want to have the PIC actually send something out through the serial lines. And so do some more setup, right? And note this, if you don't find a tab called UART1 output, close your project out, reopen it, try it again. It takes a while. And if you run it, you should see in that UART1 output window the message "Hello World" appear. Right, so it should be reading from your serial from your file in serial and then sending it out in serial, and you can see the version of what it's sending out in ASCII through this UART1 output tab. All right. So experiment 1 is just following all these instructions, but procedure, write up what you have to do in your own terms, and then observations, record what you observe, right? And don't just say, it worked the way it was supposed to. Record what you observed, okay? And then 2 experiments you get to modify the code for. So experiment 2, you're going to do the same thing as an experiment 1, but change the code so that after it reads a character, it adds 1 to the ASCII value before it sends it out. And if you run this, then in your output, instead of seeing HELLO, you should see IFMMP. Right, so it'll add 1 to each character. So that shows you know where to get into the code, where the characters that you're reading are actually being loaded into a register, and where you're actually choosing what to send out to the register. Once you've got that working, you go into experiment 3. Experiment 3, you want to make something that switches between uppercase and lowercase. So you get to use some logic here, some if statements, and basically the rule for converting ASCII characters are the following. If your ASCII code is between 41 and 5A, add 20. If your ASCII code is between 61 and 7A, subtract 20. Otherwise, leave your ASCII code alone. If you do these conversions, your lowercase characters will change to uppercase and vice versa. And so try this, make a test file with some uppercase and some lowercase and some non-letters, some spaces, some numbers, things like that. Run it and show the UART1 output window, and it should show the contents of your file with uppercase, lowercase, reversed, other characters unchanged.
This is just like the lab in Introduction to C.
Oh, is that a lab in 121?
I forgot what his name was.
Scott?
Something Scott.
Yeah.
Yeah. In that class, we made a palindromes calculator. So if you put in a palindrome, we had to convert everything to upper and lower.
Oh, cool. Awesome. Yeah, so you could actually turn this into a palindrome detector too. All right, so that's basically Lab 6, and it's the most I think it's the most complex lab in terms of there's all this stuff you have to set up to get the serial I/O working. But once you have it working, right, you've got this code here. You really need to change, 1 line for experiment 2, or add 1 line for experiment 2, and then add a small section of code for experiment 3. And that code you're going to add is just like, the homework questions and the midterm questions you've done, where it says, write a snippet of code to do the following. If WReg is bigger than 41 and less than 5A, then WReg is WReg minus 20. Right? So just make sure that you do this as an if-else. Don't do step 1 and then do step 2, because if you do step 1 and you add 20 to x, well, x is going to be between 61 and 7a, and then if you subtract 20, it's going to be back to its original value. So, if this is true, do this. Otherwise, if this is true, do that. Don't do them both. Yeah, cool. I think we are just outputting a string of bits to make the ASCIIs. So you would add or subtract the output stream.
Can you make it talk to USB like you can with RS-232?
USB communication is pretty complex, but there are a lot of devices, like a CH340, that will do translation between USB and serial. And they're, a couple of bucks to buy. And one end plugs into a USB port, and the other end has basically 3 lines, a transmit, a receive, and a ground. And that's a really easy way to do serial communication through a modern computer, because our PCs don't have serial ports anymore, but those translate nicely. And remember, everything that you're doing in your code is just being done on bytes. Right? We don't have to worry about serial communication. We don't have to worry about this business inside our code. In our code, we're going to, set things up and when we want to send a character, we're just going to take the contents of a register and move it into TX-reg. And once you do that, the character gets sent. So we get to work with this data as if it was parallel data. It's just 8 bits wide. But the hardware takes care of serializing it, or taking a serial stream coming in and turning it into an 8-bit number. All right. Any other questions?
What is RS-232 used for today? I hear it's not. It's still used for stuff.
It's largely because of these dongles that'll go between USB and serial. They all translate into RS-232. But a 0 to 5 volt version, or a 0 to 3.3 volt version of RS-232, but the same protocol. I think that's probably the main use. But you know, if you have an Arduino processor or a Raspberry Pi or an ESP32, they all have a pair of pins labeled TX and RX, and those are serial communication lines, and that's basically RS-232. So if you had a serial device, you could hook it up directly to the pin 0 and 1 on an Arduino and communicate in serial. Now, most Arduinos come with a USB port, but guess what? They have something like a CH340 to translate from the USB to these serial lines, and then you can talk through the serial port. Or if you want to...
So it's just easier and cheaper to make a microcontroller that works in serial and then sends it to a translator for USB.
Yeah, serial is a really kind of low bar, low cost of entry. For example, if you wanted to hook two Arduinos together and have them share information, really easy way to do that is through two serial lines, right? Take a transmit and receive, take a receive and transmit, hook them together, and you know, it costs you 2 pins, which is not a lot, and you can send whatever you want, bytes or words of information. And there's libraries that will take, you know, arbitrary pins and do basically, you know, this kind of thing on whatever CPU you're running, an Arduino or an ESP or whatever. And then if you want to communicate with something, you know, higher level, you can have hardware or software to do that, whether it's a USB port or a Wi-Fi shield or something like that.
So just to make sure that I understand this, the way that serial communication works is there's only 2 lines, and there's a clock line that dictates when it's reading, that there's an input from the serial, and it just reads every 8 puts.
It basically, yeah, it really depends on the protocol. So for RS-232, there's no clock line. There's an implied clock, which is determined by what your baud rate is. So both sides have to say, okay, we're going to communicate at 9600 baud. And you both, you know, have your own internal clock, and you know, so all you need is a transmit line, a receive line, and a ground, which is your common. I2C, for example, also has a clock line. SPI also has a clock line. But the basic idea is the same. You have some way of sampling, you know, a data line, and each time that you sample it, you've got the next bit of whatever information you're sharing. And usually, you know, RS-232, we're sharing bytes, but sometimes we're just sharing streams of information. We might be sending, you know, over 500 bits that you know, might be broken into chunks of 8 bits for characters, or they might be something totally different. It's really kind of up to you. It's a very fun world to play with, and it is super accessible. It used to be that this stuff was, you know, pretty hard to get into, and you'd need expensive equipment and all this kind of stuff. And if you have an Arduino, you can play around with serial right there. If you get, you know, one of these little dongles, you can play around with that. Let me show you one of these since I keep referring to it. So this is like a classic example. So that end goes into a computer, and this end comes out, and there's a 5 volt ground, receive, transmit, and 3.3 volts. And you can plug that right into a proto board and pull your signals off of that. And that chip inside there, that's the one that's doing all of the conversion. And most of these that you find, this is a CP2102, which is another good device. A lot of these that you find are bootlegged. The chips are manufactured by, someone who didn't care about the patent. And so if you try to go inside some of these chips, you find that they don't work quite the right way. There was a time when the manufacturer of these chips was putting code in their drivers that would detect if these were counterfeit and would brick them. And that upset some people. But, the chips typically cost, like $8 a piece. And I think I bought this on Amazon for like $1. I think I got 5 for $5. So something's going on. It's an interesting world.
I just did some research, and multiple forms of like serial communication, even in our computers today, eventually get translated into RS-232.
Yeah.
485 because it's just bits and bytes.
Mm-hmm. Yeah, and like I say, you're sort of the creator of the world, right? So you can use whatever protocols or approaches you like for sending information from one system to another, or coding information or things like that. There's a lot of support for things like this style of communication. So there's libraries and such. But when you're down at the assembly language level, when you're down at the level of interfacing with pins on a microcontroller that directly relate to these special function registers and so on, you can kind of do what you want. And we don't really have to do any of this fancy stuff that using this whole UART subsystem. We don't have to do that, right? We can do serial communication just using 2 pins. We could pick RB0 and RB1, and we know how to do timing, so we could simply write some code that says, okay, well, let's wait this long and let's read RB0, and if it's a 0, we'll store a 0. If it's a 1, we'll store a 1. And then let's rotate this thing that we're loading these bits into. Let's wait this much time, look at RB0 again. And you can do what's called bit banging, right? Basically just manipulate the bits by hand to either create or to read a serial signal like this. But if you do that in software, that's all that your program is doing. So we have these subsystems built into the hardware that'll do this for us. But sometimes, all you want to do right now is just send a character out or receive a character. You can just write some code, and as long as you know how to manipulate the timing correctly, you can do all of this just in software. And that can be fun.
It's really cool because you think of like languages that can be built on top of C, because C is this common ground, and whatever the application of your programming language needs to accommodate, you can just build it on top of C. But you can basically do the same here with serial communication.
Exactly, yeah. And this is one of the ways in which the lines between hardware and software start to disappear. And at some point you're doing hardware in a way where you realize, hey, I'm really doing programming, and vice versa. And that's kind of where things open up in a big way. All right, so yeah, I could geek out on that for like hours, but let's talk more about indirect registers. So this is our last big frontier. And so let me pull up a summary sheet here. Not that one though. This one. Oh, by the way, that's the transmit and receive pins for the serial port. So pin 9 is TX, pin 10 is RX. That's where you transmit and receive if you're using that subsystem. We don't have to know that for the simulator, but it's good to know. All right, so we have these indirect registers, and they go along with this file select register. And do you remember the basic setup? If, for example, we load 55 into file select register 0, then whatever we do to INDF0 gets done to file register 55. If we clear INDF0, we will clear file register 55. If we test INDF0, we will test the contents of file register 55. If we increment INDF0, we increment the contents of file register 55. And none of these things affect FSR0. FSR0 is a separate register. It's actually a pair of registers, FSR0, L, and H. And so INDF0 means the thing pointed to by FSR0. And remember, FSR0 is really FSR0H followed by FSR0L. So it's a 12-bit number because it's the address of a file register. So INDF0 refers to the thing pointed to by FSR0. And there are these other things along with INDF0. There's this post-inc 0. And so post-inc 0 means look at FSR0, see what that points to. That's the thing that we're going to operate on. And then when we're done afterwards, post, increment FSR0. Post dec 0 is the same as star FSR0 minus minus. So use FSR0 as the pointer, and when you're done, decrement it. And then pre-inc is the same thing as plus plus FSR0. Increment FSR0 first, and then use that as the address of the file register that you want to operate on. And then finally, plus W0 says take the contents of file select register 0, add the W register, and that value that you end up with, that's the address of the file register I want to operate on. This does not change FSR0. This does not change FSR0. This changes it by +1. This changes it by -1. This changes it by +1. This doesn't change FSR0. It just says, you know, do the following operation. Look at the value of FSR0, the value of WReg, add those together. That's the address that we're going to do something to. So if I say increment plus W0, it'll increment the file register whose address is FSR0 plus WReg. Alright, so let's play with this in MPLab, because a simulator's worth 1,000 words or something like that. So I already started a project here, so let's go ahead and do this simulation. I don't even know what this is called. Oh, project name. I'll call it indirect. 2, 3, 4. Okay. Alright, so I've got a project. I'm going to make a main program. So I'll do a new ASM. I'll just call it main. And I'll do my one-time funny business where I have to go to configuration and I have to say go to global options and build an absolute mode. Absolute mode basically says that it's going to store, for example, when you say go to a location, it's going to actually store that location in the coding of the machine instruction. This is what we've been doing. But there's an alternative, which is to make your code relocatable, where jumps and accesses to things are done relative to something else, and so your code can move around. I don't know why it wants to build in relative mode for me, but it just seems to be me, so I don't think you have to worry about that. Hello.
Hello.
All right, so let's write some code. So I'll include P18F1220. I'll do origin 0. And the goal here is I want to play around with these indirect registers. All right, so let's start off being pretty barehanded. Move LW 20, move WF, file select register 0 low. Let's clear file select register 0 high. And so, you know, I'm setting this 12-bit file select register to effectively 020. All right, so that's that. Let's put a 55. Oh boy, what did I do? Let's put a 55.
You're missing an end statement, I think.
Yeah, I'm not even there, but thanks. So 55 is just a cool bit pattern. It alternates ones and zeros. 55 and EE are useful that way. And then let's make a loop. So I'm going to say move WF into IND F0. And then I'm going to say increment file register FSR 0L. And then I'm going to branch back to loop. And that'll be the end of our program. All right, so let's make sure this builds first. That builds fine. I'm going to put a breakpoint right here. So what are we doing here, right? We're going to basically load FSR0 to be 20 hex. And we're going to have a loop that just continually moves W, which is this magic pattern, 55, moves W into INDF0, and then increments FSR0. So the first time that we do this move, FSR0 should be 20 hex. This should load the value of W into file register 20. All right, so let's watch how this thing works. So let me set up a watch for INDF0 and a watch for FSR0L. And I'm going to add one more thing here. So you'll want to pay attention to this. I'm going to go under Window, Target Memory Views, File Registers. All right, write this down. Window, Target Memory Views, File Registers. This is good stuff. You ready for this? Bang, there's our file registers. All right, I'm going to put this in a separate window, so I'm going to drag this tab right here. And the way that you look at this is, you know, these are registers 0 through F in this first line. The next line is registers 10 through 1F. Down here at the bottom is registers F0 through FF. And then 100 on up, those don't exist until you get to the very end. And now we're in our special function register area. So F80 through FFF, those are available. They're whatever they are. But we're mainly just going to play with these first few registers. All right, so this is a convenient way to look at the contents of your file registers as your code runs. So let me shrink this down a little bit. Let me make this big. All right, so let's build this again. We've got a breakpoint right here. Let's run it. All right, so we're clearing file select register 0 high. And we're putting a 55 into W. And you can see that just hit right up here. All right, so most of our file registers have a value of 0 right now. That's just kind of how they power it up. All right, we're about to say move W into INDF0. So what location are we going to write the value of W into? Which file register is going to get modified here? FEF. Why FEF?
It says in the address.
Oh, so that's the address of this special function register. All right, so if this was any other register, you'd be exactly right. But INDF0, remember it's got that tag, it says not a physical register. So INDF0 means the thing pointed to by FSR0. So what's FSR0 equal to? Not a trick question. What is FSR0 equal to?
20.
20, good. So when we move W into INDF0, it should get written into file register 20. Okay, that's the whole mechanism of these indirect registers. We're saying move it into INDF0, but what it's actually going to do is it's going to say, oh, wait a minute, what is FSR0 equal to? 20. Okay, so I'm going to move W into file register 20. And we step that once. Bingo, file register 20 now has our magic bit pattern 55. All right, I'm going to increment FSR0L. So when I execute that, FSR0L is 21. We're going to go back and we're going to say move W into INDF0. Now what file register is going to get written?
$21.
21, you got it.
Yeah, 21.
Go ahead and execute that instruction. Bingo, there's 21. We're going to increment file register 0L, so now it's 22. We're going to move W into INDF0. What file register gets written now? File register 22. Boom. And every time I do this, a new file register gets written. And this is the magic of arrays, right? Arrays, it's like, yeah, okay, whatever, right? When I first learned about arrays, it blew my mind, right? Because I have, you know, the same statement, but it's doing something fundamentally different. I keep executing this line 10, move WF into INDF0. But, you know, when I did this now, it changed the contents of file register 31. The next time I do it, it's going to change the contents of file register 32. That's magic, right? This is the beginning of all good stuff that happens in computers. And yeah, it's got an ASCII cheat sheet on the side, which is awesome. All right, so 3 lines of code. If you can make peace with these 3 lines of code, you're done with the course, right? This is the last big topic in the course. This is the essence of it, right? If you can grapple with these 3 statements and understand why they're doing what they're doing, you're basically good to go. All right, so let's make it a little more interesting. Let's move W into file register INDF, and then let's add a 1 to the W register. Basically the same code, except we're going to change the value of W each time that we go through this. So the W register is equal to 55. We're going to move that into INDF0. There's our 55 again as usual. Got it written to location 20. Now we're going to go ahead. We're going to increase W to 56. We're going to branch back to loop. When we move W to INDF0, it's now going to write file register 21. And so now we get a V written into this register 21. And each time we do this, we're changing successive locations, and we're loading a different value into those locations. And so we can just kind of have some fun with that. And if I'm brave, I can just run this and pause it. And now we've got, whole bunches of values written into our file registers. Because, when FSR 0 gets high enough, it rolls back over to 0, and we start, writing over values again. Now, my code actually went ahead and it also overwrote some special function registers. No, it didn't. It didn't. We're okay. So FSR 0 is an 8-bit register. And if I keep incrementing FSR 0, it will increment up to 255, and then it'll go back to 0. Right? And so the only values of FSR 0, the high part and the low part, are 0, 0, 0 through 0FF. So it's only affecting these registers up here.
What happens when you put in like the null terminator or something like that?
It's just a 0.
Oh, it is?
Yeah. So I could do something like, let's put a 0 into the W register. Without the typo. Let's build that. Let's run it. Alright, so the first time W is 55, we write that into here. But the next time that we go through, it's just going to write a 0. And we don't even see it turn a color because, it's the value that was already in there. But if I load, say, non-zeros into there, and I run this, you'll see where it wrote a 0 in place of the contents of file register 23, and the next time it writes a 0 in place of the contents of file register 24, and so on. So zeros are special characters when we are in C and we're thinking about arrays of characters and we're using them as strings. There's a convention that 0 is called a null terminator. It marks the end of a string. But it's really just, another pattern of bits that, happens to have all the bits be equal to 0. And this ASCII column over here, this is pretty standard for looking at hex dumps of information. If the character has an ASCII code that's printable, it will display it with the ASCII code. Otherwise, it will just display a period usually. Say it's a non-printable character. So ASCII code 11, that's character 17, that's not printable, so it comes out as a dot. Same with 0, but 55, that's a letter U, so we see that. All right, so let's just talk about some questions about this first. Because like I say, seriously, like these lines of code right here, that's it. If you can understand that, you're golden. And then we're just going to talk about some embellishments and some bells and whistles on this stuff. So one embellishment is the LFSR instruction. So up here, what did we do? We loaded a 20 into W, put that into FSR 0L, and then we put a 0 into FSR 0H. And the goal there was, to initialize this pair of registers, FSR 0H and FSR 0L. But there's a 2-word, 4-byte instruction that will let us do the same thing. And it works like this. We can say load file select register 0, comma, hex 20. And that will load, you know, the 12-bit version of this number, hex 20, into LFSR 0H, LFSR 0L. So if we build this up and we run it, so FSR 0L happens to be 24 right now. When I execute this load file select register instruction, that changes FSR 0L to be 20. It would also change FSR 0H to be 0. But I'm not showing that one. And then the rest of this code proceeds as before. Keeps writing 55 into memory. Alright, so that's one embellishment, the load file select register instruction. And that's just one of the instructions in table 20-1. Alright, another option, post inc 0. So instead of moving into INDF 0, we can move into post inc 0. And now I'm going to get rid of this increment FSR 0L. So now I'm down to a 2-line loop. But this is going to do basically the same thing as our previous code. So W is equal to 55, FSR 0L is equal to 32. Okay, so watch what happens when we do this one instruction. Two things are going to happen. We're going to see two things turn red. So let me step this instruction once. So what just happened? Well, we loaded the contents of W into file register 20, because that's what FSR 0 was. And we also incremented FSR 0 to be 33, 21 hex, instead of 20. So we got 2 for 1. When we use post inc 0, it does an indirect reference, and when it's done, it also increments FSR 0. If I execute that again, it writes a 55 into register 21, and it increments FSR 0 to be 22. And this is useful if you had more than 256 file registers. If we wanted to increment FSR from say, 0FF to 100, right? Just incrementing FSR 0L doesn't do that. But using this post inc, it knows it's a 12-bit number, and if you go from, say 0FF and increment once more, it'll go to 100. If you're at 1FF and you increment, it'll go to 200, and so on. And this one can get us into trouble because, when we get to, let me go ahead and seed a value into here. Let's put an FC into here. And let me come down to the bottom here. Alright, so it just wrote a value into FD. You can see that right here. And there's FE. And let me make this a little bigger. Alright, so it's just written a value into FF. And FSR 0L just got incremented to 0. So the next time that I execute that move instruction, we would expect that file register 0 will get changed, but it didn't. And the reason it didn't get changed is because now FSR 0H is equal to 1. So FSR was looking at file register 100, and now it's looking at file register 101. And after it does that, it'll look at 102 and so on. So these are not these file registers anymore. These are these file registers that don't exist. But nonetheless, our code is trying to modify them, and it becomes a no-op. But if I let this thing run, eventually FSR0, H, and L are going to get to values where we do have special function registers. And these are going to start getting overwritten by 55. And that's going to cause all kinds of chaos, and it's probably going to crash our machine if I just kind of let it run. But let's go for it. Right, so here's our special function registers, and we got a bunch of 55s written in there. And these are things like, you know, intcon and trisb and addcon1, as well as things like, you know, program counter high and low, stack pointer high and low. And chances are, you know, if I did this on a physical chip, something would get corrupted and it would end up resetting the processor. The other thing that can happen here is you can actually use indirect registers to modify these indirect registers, right? Because these things and this thing, these are just special function registers. They have addresses. And if I use INDF0 to modify INDF0 by setting FSR0 to the address of INDF0, I can get unpredictable results. Usually not a problem in simulation, but something to be aware of. So, you know, with these registers, you're basically able to tinker around with more or less arbitrary locations in your file register memory. Not as dangerous as tinkering around with your program memory, but still, you know, something that can give you weird results. All right, so that's basically all there is to know about these. So let me just tweak this a little bit more. So let's go around and let's do pre-inc 0. And let's build that and run it. All right, so file select register is equal to 20. And we're going to move W into pre-inc 0. So what file register do we expect is going to get modified in this case? Take a shot.
Would it be 19?
It'll be 19 or 20 or 21. It's going to be one of those. It's pre-inc, so it's going to increment FSR 0. And the pre part says do the increment before you use what this is pointing to. So right now FSR 0 is 20. So this says increment it to 21 and then move W into file register 21. So if we execute that instruction, we'll see file register 21 got changed. The other option is post dec. And if we do post dec, that says, you know, decrement file register 20, but decrement after you've used it. So this first move should move into file register 20. That's that right there. But now FSR 0 has changed to 1F. So the next time that we execute this, we see 1F changes, and then 1E and 1D and so on. There is no post decrement instruction. Or there's no pre-decrement instruction. There's a pre-inc, post-inc, post-dec, but there's no pre-dec. I don't know why. You only got so many instructions. All right, so the last embellishment is this plus W. And so let's do something like let's put a 4 into the W register. And instead of moving, I'm just going to use set F. So set F will set a file register to be FF. So it's an easy pattern to detect. And let's set F plus W0. So we'll build that, we'll run it. All right, so W is equal to 4. FSR0 is equal to 20. What file register location is going to get affected by this instruction? W is 4, FSR0 is 20.
The special function register after reg?
After what reg?
Wherever in special, the special function register where WREG the reg is.
Ah, good idea, but not exactly what it does. But that would make sense also. What's the contents of the W register?
Oh wait, would it move whatever's in the W reg plus 1 to where INDF is? Not INDF.
Closer. So here's what it looks like in C. So take the contents of the file select register, that's 20. Contents of WReg is 4, add them, that's 24. This is the thing pointed to by 24. It's the thing at address 24 in the file register memory. So this set instruction should set file register 24, this one right here. So execute that, there's 24. So take the file select register contents, take the W register contents, add them. That's the address that we're going to work with. And so in here, if I say something like add a 5 to the W register, what's this going to do? Well, if the W register starts off at 4, FSR 0 is going to be 20. We're never going to change FSR 20 here. It's always going to be FSR 0. It's always going to be 20. But 20 plus W is 24. This should set file register 24. There we go. Now I'm going to add 5 to the W register. 4 plus 5 is 9. So now when I do plus W0, it's going to be file select register, which is 20, plus 9. This is going to change file register 29. If I do this again, W will increase to, let's look up here, it's an E. So this will change 20 plus E to E. There's file register 2E. So now I'm changing every 5th file register. But more importantly,
incrementation, that's cool.
Yeah. And I'm doing it without changing FSR 0. FSR 0 was initialized to be 20 and it never changes. And that's really useful. Alright, so that's the plus W0. And then the other thing to note about this is, there's another set of registers, which are INDF1, FSR1, PostInc1, PostDec1, PreInc1, plus W1. They work exactly the same way, but they're completely independent of these. And then there's a third set of registers, INDF2, FSR2, PostInc2, etc. Completely identical behavior, but completely independent of the ones and the zeros. So we have 3 sets of these registers that we can use to do these indirect references. And they're all independent of each other. All right, so send me an attendance ping, and we'll take a 5-minute break, and then I want to come back and I want to talk a little bit about why we have these mechanisms, what they're useful for, how they get used typically inside a computer, and then we'll move on from there. So let's come back at All right, hey, welcome back. All right. So questions? All right, so why do we have this? You know, pick is a risk machine. It's only got so many resources, and we've got, you know, 1, 2, 3, 4, 5, 6, 7 times 3 is 21 special function registers just dedicated to doing these indirect references. That's a lot of resources. I mean, we only have, you know, 128 SFRs, and some of these don't exist. So maybe 100 FSRs, and, you know, about a quarter of them are being spent on this indirect referencing. And why is it so useful? Well, you know, one example is arrays. And that's basically what we were just seeing in this plus W example, right? So when we have code that says, you know, do something to plus W0, what are we actually asking our processor to do? So if FSR 0 is equal to 20, plus W0 means file register 20 plus whatever the W register is. So imagine we had an array of characters, or bytes. And so here's our file register memory. So there's 00 through 1F. Here's hex 20, 21, 22, 23, and so on. If I set W equal to 0, then when I do something to plus W0, it does that to this file register right here. The register at FSR0, which is 20, plus W. If I put a 1 into W, then when I access plus W0, it refers to this file register. If I put a 3 into W, then plus W0 refers to this register. So if I have some kind of character array stored in memory starting at location 20, and I think of this in terms of C, as, you know, an array that I can index with an index of 0, 1, 2, 3. If I want to index a particular element, I just load that index into W and I use plus W0. And it basically says, you know, start at this address and go forward by W locations. And so that's super convenient. So if I wanted to do a string length function, right, how do we find string length in C? Well, we start with the first character and we move character by character until we get to a null terminator. So I might do something like this. So initialize FSR0 to the address where your string begins, which is also, you know, the address of the first character. And Let's put a 0 into our W register. That's going to be our index. And I'm just going to say something like move file register plus W0. Now when you move a file register to itself, it doesn't do anything. It doesn't change anything except update the status bits. And so I could say branch of 0, done. So if the register at this address is equal to 0, that's the null terminator, I'm done. Otherwise, let's increase W and go back and try again. So this will look at file register 20. If it happens to be 0, I'm done, and my string has length 0. Otherwise, I'll set W to 1, go back and check character 21. If that's 0, I'm done, and my string has a length of 1. If it's not, I'll increase W to 2, go back and try this again, and this will be character 2, right? The character at file register 22. And so at done, wreg is the string length. And I hardwired it, you know, for an array starting at location 20. But if I was going to start at some arbitrary location, right, I could put this into a function that, you know, you set the W register equal to the location of your first character, and then do all of this. And when you return from here, W register has a string length. And we've got our first C library function written. So these are useful for moving through an array. And suppose we wanted to copy one array to another. So let's say copy 9 characters from file register 40 to file register 70. So I'll use file select register 0 to be the source. I'll use file register 1 to be the destination. This will tell me how many times I want to loop. I want to copy 9 characters. So here's my loop. All right, so how do I copy the byte from file register 40 to file register 70?
Each iteration of the loop, you'd take the item at the file location in LFSR 0, move it into reg, and then move that specific item into the reg of the destination bit, and then increment both, right?
Awesome. So I could do something like move f indf 0, comma w, move wf indf 1, and then I could do increment file select register 0L, increment file select register 1L. And I want to count a loop to do this, you know, 9 times. So I can't use W here because I'm munging W in these operations. But that's basically the essence of it, right? This moves from first time through file register 40 into W, and then pushes W into file register 70. And then it'll increase these to be 41 and 71. So this will move from file register 41 to W, and then W into file register 71. Can I do these operations without using my W register?
FF?
Use moveFF. That's a powerhouse instruction. moveFF, INDF0, INDF1. Now we got these two for the price of one, and we're preserving our W register. So then we can do these increment instructions, and then we can say decrement W reg, and branch if not 0, back to loop. There's one other embellishment we can make on this, and it's finding a different way to do these things. Any thoughts? I'll put this down for reference. So what's our other way to increment FSR 0 and FSR 1?
We could do the posting 0 and posting 1.
Yep.
Yeah.
So check this out. Single instruction. And that does all four of these things. Alright, read the contents of FSR 0. Use that as the file register you're moving from. Read FSR 1, use that as the address of the file register you're moving to. Go ahead and do that move, and then increment FSR 0 and increment FSR 1. So this is a really, really succinct little loop to write. Right, a move F, decrement W reg. If it's not 0, go back and loop again. And that'll move 9 characters from source location to destination location. So this is where Darth Vader would talk about the power of the indirect registers. Right? They're really, really useful like this. You could use add. Totally. We could do this a totally different way. We could initialize FSR 0 and 1 like this, and we could move FF plus W0 plus W1. Well, the first time we do that, it would move 49 to 79, and then when we decrement W reg, and we do this again, it would move 48 to 78, and we would keep doing that. It would move from the end to the beginning, right? But that would get us there as well. So we could say move FF plus W0.
This pertains to CISC.
Sure.
So if we say had a C program that was using pointers that compiled down to an executable that your computer could run right now, would there be any limits to how many of those pointers you could have because they turn into indirect registers at some point?
So depends on your architecture, right? But technically no. We happen to have 3 of these indirect register sets here. If we wanted to do something that involved multiple arrays, what we'd have to end up doing is, store FSR 0 into a pair of temporary registers, and then read, from another set of temporary registers back into FSR 0. So we would have to keep reusing these, just like we have to keep reusing the W register, right? W register is the only way we can load a literal, so if we want to load a literal, got to use the W register. If we're using W for something else, we have to save that value somewhere and then get it back later. Same thing with this. But the PIC 18F1220 gives us 3 of these, right? Which is, pretty useful. Certainly you want 2 of them so you can do this kind of thing. And having the third one is kind of bonus. But on a CISC machine, typically what you find is, you might be able to use any register as an indirect register. So like VAX architecture, for example, you could take any register and say, this is a pointer to a memory location. And you could use that to indirectly access memory. or you could directly use a memory location to access another memory location.
I bet you could kind of simulate it here too. If
Mm-hmm.
you just have the 4 registers where you could say, I want such and such amount of registers to be nothing but pointers, and every time I load one in, I load it into this register
Mm-hmm.
as the multiple pointers.
Yeah, yeah. And you can set up conventions to do all kinds of things, right? But the hardware has to support, at least one of these indirect registers. If it doesn't do that, there's almost no way to do any of this stuff. There's almost no way to write a line of code that will, sometimes affect one location and sometimes affect a different location. Really, the only other way that you can do that is to get into self-modifying code. And I think it was Wilkes who first proposed the EDSAC architecture, which was self-modifying stored program, and that was one of his first examples as to why this would be useful. He implemented an array with it, because the earlier machines were hardwired. There was no soft part to the software. This program was, a collection of cables and knobs and things like that, and so they proposed this soft version of a program, and one example they gave was, you can change the operand in this instruction to point to successive values, and in that way we can have the same code operate on successive locations in memory. And it was an early implementation of an array, right? That was one of the justifications for moving to a stored program. All right, one other comment on this, and if you're doing CSE 224.2.3, we'll get into some of this off and on throughout the sequence. But when you write a C program, let's say we have some function called fun, and it's got some integers I, j, and k. Okay, these are local variables, which means they're, locations in memory where we can store numbers while this function is running. But after we return from this function, these variables don't have to be preserved anywhere. In fact, we would like to get rid of those variables and reuse the space in which they were stored. And one way we can do this is to initialize FSR0 to point to some area of memory that we're going to use for local variables. And we can just think of this as an array where the thing at this location will be I, the thing at the next location will be j, the thing at the next location will be k. And now if we want to do something with j, what do? We put a 1 into the W register, and then we use this plus W0. And that's going to get us to our variable j. And then if we want to do something with the variable I, we put a 0 into W, and now plus W0 refers to the variable I. And so a lot of C compilers and operating systems will basically treat your local variables like an array. And they get stored in a section of memory that can be reused once you leave the function. So this would be something called a stack. It's a different stack from what we have on the PIC. But the general idea is we have a base register, something that points to the beginning of some location of memory. And then we just have fixed offsets, like if I offset 0, that's I, if I offset 1, that's j, and so on. If we want to really brush off the 121 neurons, if you remember the structure statement in C, structures are a way to say, hey, I've got a variable named blah, but it contains, 3 integers, a double, and a string of characters. And it's all part of one super variable called a blah, right? Well, the way that we access those different fields are, again, we take something like FSR0, point to the beginning of this structure, And then our first integer is, offset by 0. Our next integer is offset by 1. Our character array is offset by 17, and so on. So these things are useful when you start thinking about like compiling from a high-level language like C into assembly language. These are there to support that compilation process and make it easy to write code that will, achieve the behavior of your C program in PIC assembly language.
I did a little experiment on my own with C where I wrote some netcode for a video game with C structs, because it's just sending a single, like if you put a name, a last name, and an age or something in a struct, it's just going to pass all 3 of those variables successively in just one little package. So you don't have to like de-stringify and stringify a JSON. It's just that quick.
Yeah, cool. And we'll talk about some of that stuff in the CS sequence if you're a CS major, and we'll be revisiting this stuff in that context. And if you like, here we'll just do something for fun. Alright, so there's a totally random C program. If you compile with a dash uppercase S switch and also a dash C saying just build this up to an object module, you end up with this haha.s file, which is the assembly language version of your C program. Now, I did this on my laptop, which is an x86 machine, so this is x86 assembly language. And it's a complex instruction set, right? But here's the literal 5 that I believe we were moving around in our code. But if you do this on an Arduino, right, or a Raspberry Pi, or a PIC processor, you get a different assembly language program depending on your underlying architecture. If you do this on a Pi, you'll get ARM assembly language code, which will look closer to a PIC. And if you do this on the PIC, so MPLab has a crude C compiler built in, and you can compile code and actually see the assembly language that it trunks down to. And so that can be fun. So yeah, GCC dash lowercase c dash uppercase s, and that gets you on the air. All right, well, we got about 15 minutes, so let's talk about floating point. And the idea of floating point is, we talked about this a little bit on Tuesday. Basically, the setup is we want to be able to represent numbers that are very big or numbers that are very small, meaning, much smaller than 1 or, much bigger than 4 billion. And we use scientific notation as humans because it only takes a little bit of space, right? If I'm trying to write down my observations in a laboratory experiment, so I measure, how much power my flux capacitor is drawing, and it's, I don't remember the number, but 3.2 gigawatts. So 3.2 times 10 to the ninth. And then I measure the Planck constant modified by something else, and I get some very small number, and it's 5.72 times 10 to the negative 85th. Really, really, really tiny number, very close to zero. And then we measure, the distance to something else, and it's 6.5 times 10 to the 147th. And the values represented here very wildly, right? This is, 10 to the 200 something times bigger than this number. But I can physically fit them in this amount of space on the page of paper. So when we're trying to store numbers that vary wildly in size in a fixed amount of bits, right, which is what we're dealing with because we're trying to store these things in file registers or W registers or whatever, to put them in a fixed amount of physical space of bits, we need a way to do some kind of coding so that whether it's a very large number or a number very close to zero, it always takes the same amount of space. And we're going to concentrate mainly on a 32-bit representation. And we use something like scientific notation. We basically have a mantissa. We have an exponent. And we have, for us, base 10. Now, if we do this in a computer, we're going to use base 2 because everything's binary. But we're going to do exactly the same thing. We're going to store a mantissa, we're going to store an exponent, and our number that we're representing is going to be our mantissa times 2 raised to that exponent. So let's say I want to store the number 0.125. Well, this happens to be, 2 to the minus 3. So this would be 1.0 times 2 to the negative 3. So I would store a mantissa of 1 and exponent of minus 3. If I want to store the number 18, well, the number 18 in binary is 168421. So it's this times 1, which is 2 to the 0. But when you learn scientific notation, right, here's this number, 6.5 times 10 to the 147th. I could also write this as 65 times 10 to the 146th. I could write it as 0.65 times 10 to the 148th. How do we know that this is the correct way to write it and that these are going to get us frowny faces from our teacher? What's the rule we're using implicitly when we write scientific notation? And yeah, both numbers are signed.
There has to be something like a whole number to the left of the decimal and a number to the right of the decimal.
Exactly.
Yeah.
So here the decimal point is 2 digits from the end. Here it's before any digits. Here it's 1 digit to the left. And so this is normalized, right? And you lose a point for these, and the teacher says you have to normalize your answer. So this is not a normalized representation, but we can move the decimal point. It's actually called a radix point because we're not in decimal. And we could also say this is 1001.0 times 2 to the 1. Or 100.10 times 2 to the 2, or 10.010 times 2 cubed, or 1.0010 times 2 to the 4th, or 0.10010 times 2 to the 5th, and so on. This is the normalized form.
Could we also, if we wanted to, just beyond using this for decimals on the pick, we could just use this for much larger math too.
Yeah.
General, right?
Yeah. And there's lots of ways to do this, and in the earlier days of computing, lots of companies did this their own ways. And eventually this was standardized to something called IEEE 754. And it prescribes a particular way to do this coding. And that's what we're going to talk about today and on Tuesday. Alright, so if we want to store the number 18, we would write it in this form, and we would say, okay, the mantissa is 1.0010, and the exponent is 4. And if we store those two pieces of information, this number and the number 4, we'll get back to the number 18. If we store the number 1 and the number -3, we get back to 0.125. And so if you look in your book, page 180, there's a nice picture of IEEE 754. So it's a 32-bit representation. This first bit is the sign bit. A 1 means the number you're storing is negative, 0 means it's positive. So that's like, the plus or minus sign we put on paper. Here's the 8 bits of the exponent, and here's 23 bits for the mantissa or fraction. And there's just a few details to worry about. And, we got 7 minutes. We can go about details. So a few details. First of all, the exponent is stored in what's called excess notation. There's a bias of 127. So whatever exponent you want to store, add 127 to it before you store it. So if I wanted to store an exponent of 4, I would actually store 131. If I wanted -3, I would actually store 124. So the bit pattern you put in here is actually your true exponent plus 127. That's just, it works out well for some things to do that. I could store a 2's complement representation of my exponent, but the decision for the standard was take your exponent, add 127, that's what gets stored here. Alright, so that's one detail. The other detail is this fraction, the mantissa part. And this is a really clever trick. So we said this was a normalized form because I had a number to the left of the decimal point. I had exactly one number to the left of the decimal point, right? Well, this form down here, hey, I got a number to the left of the decimal point. Why did I lose points for that? Well, because you can't have just any number to the left of the decimal point. You need a number, a digit, bigger than or equal to 1 and less than or equal to 9. I mean, here I had some stuff to the left of the decimal point, but I had the number 65, which is like bigger than 9. And here I've got a 0, which is less than 1. So in decimal scientific notation, the one digit to the left of the decimal point has to be at least 1, and it has to be less than 9. Less than or equal to 9. That digit, we can also think of it as being bigger than or equal to 1 and less than 10. And this 10 is 10 because we're working base 10. That's our base. So if we extend this to base 2, this digit to the left of the decimal point has to be bigger than or equal to 1 and less than 2. Well, if you have an integer that's bigger than or equal to 1 and less than 2, do we know what that integer is?
It's 1 point something.
It's got to be 1. We know we're not allowed to have a 0 to the left of the decimal point. All of our digits are either 0s or 1s. If we're not allowed to have a 0, we're going to have a 1. So when we normalize our fraction, we know this digit is always a 1. Guaranteed. Well, same thing we've seen in the PIC processor. If we know this digit is a 1, let's not waste bits storing it. So the fraction that you store in this notation is everything to the right of the decimal point. We don't put that first 1 into this fraction. Why? Because we only got 23 bits of fraction. let's get as much use out of them as we can. So if I wanted to code the number 1.0010 times 2 to the 4th, this is the number 18, I would store the exponent as 4 plus 127 equals 131, and I would store the fraction as 0010. And since it's positive, my sign bit would be a 0, which means positive. So now it's just a matter of taking those values and putting them into this template. Put a 0 right here. Put the decimal number 131 into these 8 bits of exponent. And then store the fraction 0010 and so on and so forth. So sign bit is 0. 131 is 128, 64, 32, 16, 8, 4, 2, 1. That's your exponent, and then the fraction would be 0010. And a bunch of zeros going off forever like that. So this would be the floating point representation of the number 18. And if we were to write that in hex, this is a 4, this is a 1, this is a 5, and these are zeros. So 41500000. We got about a minute. Let me see if we can get lucky. So that's our number, but that's written in decimal. So let me try this. So let's do 10999 56 224 and convert that to hex. And 4190000, and I made a typo here. 1001 is actually 9, 8 and 1. So 4190000 is this number in decimal, and that's this constant that's defined in the assembly language. Right? It makes this 32-bit number like this, and that's LC0, and then LC0 eventually gets moved into what corresponds to our variable x. All right, so that's a quick run through. We'll talk a little more about this on Tuesday, but you should be able to do those extra homework questions that we skipped in the homework. Those 3 questions on floating points. So take a shot at those and ask questions about them. And then the only other thing to talk about on here is 64-bit version, so double precision, which uses more bits for exponent, more bits for fraction. And that gives it more range and more precision. And then these special numbers that we use, because, for example, if you want to write scientific notation for a 0, well, you know, it would come out to be something like 0 times 2 to the something, right? There's no way to normalize this. We can't shift our decimal point left or right to put a 1 to the left of the decimal point. So we need a special representation for 0. And so there's special representations for that, but also for infinity, and also for representing something that's not a number. Like if you take the square root of -1, and some other things like that. So we'll play around with that a little bit more on Tuesday, and then we're pretty much in the home stretch. So Tuesday we'll talk a little bit about the final exam, which is on Thursday, and if you have any questions, we should definitely review what we've done, but we'll talk about the last homework. I'll get that back to you, and we'll talk about Lab 5 and go from there. So, all right, cool. We're a few minutes past, so thanks for sticking around. Shoot me one more attendance ping. Let me know you're here at the end. And I will see you in lab hours in a few minutes, or have a good weekend, and I'll see you next week.
See you next week.
Have a good one.
Thank you.